All right, so next lecture in chapter 5. Actually, I'm going to knock out two sections in one, so this will be the material that you need for 5.3 and 5.4. So we are going to get this done, you guys. We're getting close. So to begin with, I have an exercise for you. I have posted the page that you can see in front of you on the screen. I've posted that to Teams. I would like you to go and download it, and let me give you some instructions. So I'm going to define a function, g of x, and g of x is going to be the integral from 0 to x of f of t dt. And I've changed the variables here because if I kept 0 to x of f of x dx and you plugged in x equals 1, then you would get the integral from 0 to 1 of f of 1 d1, and that wouldn't make any sense. And so just notice that, for example, g of, let's do maybe one example, g of 1 is the integral from 0 to 1 of f of t dt. Here's f pictured. Okay, the integral from 0 to 1 of f of t dt, you know, in this case is going to be this area. You can estimate that. Looks to me to be about 1. So, for example, g of 1 is about 1. Remember, when you get here, the area below the x-axis is going to be considered negative area. So what I want you to do is go through and estimate each one of these pieces and then use them to sketch a rough graph of, that's not what it looks like, of this function g of x. And this function is going to be critical for what we do. So pause the video, go ahead and do that, and then when you're ready, come back and watch, let's watch what I've worked out as well and check and make sure that you got it. Okay, so g of 0, I instantly know is 0 because it's the integral from 0 to 0. G of 1 is just this area right here, which looks to me to be exactly 1. So I'm just going to say equals 1. G of 2 is going to be the area out to 2, so this area, so that should be exactly 3. G of 2 is 3. G of 3, okay, this one's a little harder. G of 3, we're going to go out to here, so we're going to get this area. So we have the 3, and then it looks to me like we're going to get more than 1. I'm going to say like 1.2. So this is going to be roughly 4.2, whatever, just make a rough guess. G of 4, we're going to lose. This area is negative area, and then we're going to, it's the same as this area. So we should be back to 3. So G of 4 should be 3. And then G of 5, we're losing that again. And so G of 5, well, we were at 3, we're losing another 1.2, so 2. So I'm going to say this is G of 5 is like roughly 1.8, something like that. So now we can go ahead and graph this. So G of 0 is 0, G of 1 is 1, G of 2 is 3, G of 3 we said was like 4.2, G of 4 was back to 3, G of 5 is roughly 1.8, so somewhere in there. And so this function, assuming it's continuous, which it is, looks something like that. You can kind of do your best to fill it in. That's, oops, I didn't mean to do that. I have to switch to partial eraser here. Fill it in. And so here's the deal. We might not like this function too much, this function g. This is a graph of g of x, because its construction, its definition is kind of strange, but this is actually the key to unlocking what's known as the Fundamental Theorem of Calculus. And so let's continue now and see what we can discover about this function and what we can learn from it. So again, how do we define it? We defined it as the input to our function, x, goes on the x, it's the bound, the upper bound of the integral, it goes on the x-axis. You're integrating from 0 to whatever x value that you plug in, and then you compute that integral. So we switch the letters here just to avoid notational disasters. All right, so let's see if we can work through this a little bit more generally. So we're going to start off with a continuous function. Let's switch colors. Let's be blue today. So let's let f be a continuous function on a closed bounded interval. Then we can define a new function, this g of x, and it's the integral from a to x of f of t dt. And please realize that the domain of g of x makes sense from a all the way out to b. If f is continuous on a to b, then you can plug x values between a and b in. Okay, so for example, let's sketch a little picture right here just to make sure this is all clear. So here is my f of x, here's my a, maybe here's my b, and you pick some x value right here, then when you compute g of x is equal to the integral from a to x of f of t dt, you're going to get this area right here. So g of x corresponds to that area, just like what you guys did before. And again, when you're plugging in a specific x value, so this might be like x equals 5, so you would go from 0 to 5. This is all definite, and you can compute it hands-on. So our goal is to study g of x, and we're interested in, well, this is calculus 1. When we have a function, what do we do with it? We compute its derivative. So we're interested in g prime of x. All right? And so just to help us see this picture and to see what's going on, we are going to go ahead and assume that f of x is greater than or equal to 0. And this means we can interpret g of x always as actual area. It's not going to dip below the x-axis, and under our assumption. It can actually, but for the purposes of seeing and understanding, let's assume that it's positive. That way, whenever you see like g of x, then you know that's a certain area. Okay, so let's zoom in on g of x a little bit. I'm interested in capturing a little piece of area. So what I'm going to do is I'm going to pick an x value right here. Here's my x value, and I can certainly plug this into the function, and I get out this height. This is going to be height f of x. So far, so good. Then I'm going to go for a little walk. Here we go, and I'm going to go out to x plus h. So I went out a distance of h, and I can plug this in, and I'm going to go ahead and form a rectangle here. Okay, and I've got a rectangle, and of course this distance right here, that's a very bad wiggle. Let's try another one. Much better. This distance is exactly h. And so I'm interested in this little piece of area, and I want to try to capture it two different ways. Okay, so this little piece of area right here, and I'm going to go, let's shade it. I have this fancy highlighter. If you have a fancy tool, you might as well use it. Don't let it sit and get old and never be used. So let's use this fancy highlighter here. So we'll do that. And okay. All right, so now we can zoom back out. So I'm interested in this area two ways. I want to estimate it, and then I want to compute it as best I can. So first off, if I want to estimate this area, gosh, it's pretty clear what to do. This area is close to this rectangle. If you were paying attention back in the first lecture, then you saw that, well, we can estimate this by just saying the height times the width. So on the one hand, this piece of area, let's call this area A. On the one hand, we can think about A is approximately, it's not exactly, it's approximately h times f of x. Do you agree? Just a rectangle. This area A is not exactly h times f of x, but it's close to h times f of x. Close enough. Now, the second way I'm going to compute the area A is sneaky. I'm going to make use of this function g. So remember, we can think about g of x as the integral from a to x of f of t dt. And so I'm going to say, okay, I can compute the area from a, let's use a highlighter, from a out to x plus h. I can compute that area, right? Then I can compute the area from a out to x. And if I subtract the blue area from the red area, I'm going to get the green area, which is exactly what I want. So let's do it. I can say, okay, the area A here is going to be, well, it's going to be g of x plus h. That gives me this big area going out to here. Okay, then I'm going to subtract this little area in here, and I'm going to be left with exactly a. So a is g of x plus h minus g of x. Okay, and so now I know something, right? I'm going to put these together. I've computed the area two different ways. That's how you do mathematics. You look at the same problem from multiple perspectives, and you're able to draw connections. And all of a sudden, I realize, oh my goodness, that's not how I want to write. I realize that g of x plus h minus g of x, that's roughly equal to h over f of x. And now I'm going to move the h over, so I'm going to say, okay, so g of x plus h minus g of x over h, this is roughly f of x. And you should be like jumping up and down in your seat right now. What is that? I'm not going to highlight it, otherwise you can't see it. What is this? If you let h go to 0, what do you get? You get out g prime. And by the way, as h goes to 0, this h of x is getting closer and closer and closer to the actual area. It's getting more and more accurate, right? As h is getting smaller, then the error gets, of course, our area gets smaller too. The point, though, is this fascinating connection here. So we can see that the limit, I'm going to squeeze it in, the limit as h goes to 0, you know what, let's hold on. Let's write it like this in blue, and let's say that g prime of x is, by definition, the limit as h goes to 0 of g of x plus h minus g of x all over h, and we're saying from the picture that that's just f of x. Whoa, so the derivative of this strange area function is just the inside function. That's what we discovered, and actually that has a name. This is called the Fundamental Theorem of Calculus, Part 1. And yes, there's more than one part. Here's what it says. If f is continuous on a closed bounded interval, then this function g of x, defined in this way, a to x of f of t dt, this function g of x is, I've got my page open, is an antiderivative of f of x, i.e., what are we really saying? G prime of x is just f of x. How cool is that? Well, I think we should stop this video, and then we'll do examples in the next one.